Hello everyone, I must say that it's really strange to make this kind of presentation in pre-recording, and I really hope that soon we'll be able to meet in person in a conference somewhere. Well, I'm Vincent Jacques, I'm working at Laboratoire Charles Coulomb in Montpellier, and this is in the south of France, and my group is essentially focused in the development of new tools to measure magnetic field at the nanoscale. If you think about spatial resolution of any kind of sensor, it's intrinsically limited by its size. So natural strategy to improve the resolution is just to reduce the size of the sensor. Along that direction, it's quite natural to think about one of the smallest objects that we have in our labs, which is a single atom. So now imagine that you have a single atom that you can isolate in your experiment. This single atom has some electron spin sublevels, for example, spin up and spin down. And you can also have the tools to make the spectroscopy of this single spin and measure such an electron spin resonance spectrum that enable to precisely measure the energy difference between the two sublevels. If now there is a magnetic field that is applied, then owing to the Zeeman shift, there is a split of the electron spin sublevels, and as a result, a shift of the electron spin resonance frequency. And what is interesting here is that the shift, the Zeeman shift here, is directly proportional to the magnetic field at the location of a single atom. So you have somehow a quantitative measurement of the magnetic field within a detection volume that is given by the size of the atom. If you want now to make a microscope, you need to integrate this single atom in a scanning probe unit, for example, at the apex of the tip of an IFM. This was proposed in 2005 by Chernobrot and Bergman, and it was realized few years after that NV defect in diamond is an ideal quantum system to bring these ideas to reality. So in this talk, there will be two parts. In the first part of the talk, I will just briefly give you the main properties of NV defect in diamond and show you how we can use this quantum system for magnetic field imaging. In the second part of the talk, I will discuss one particular application, which is imaging non-collinear spin textures in antiferromagnetic material. So I start with the NV defect, and the NV defect is a point defect in diamond that corresponds to the association of a nitrogen atom here, a nitrogen impurity that is associated to a missing carbon atom, a vacancy in a neighboring lattice site. And this complex here will lead to the formation of discrete energy level within the band gap of diamond. This defect is optically active, so that you can excite it with a green laser and you will collect some photoluminescence with a very broad spectrum here centered around 700 nanometers. So this defect is known since more than 50 years, but it was only in 1997 that it was detected at the single scale at room temperature. So what you see here is a photoluminescent scan of a natural diamond sample, and the spots that you can see correspond to the emission of photons by single NV defect in diamond. Since that time, there have been a lot of efforts to try to control the creation of this defect in diamond, and a promising solution is to use nanoscale ion implantation. So it is pretty simple here, is just to shoot nitrogen ions inside diamond to create NV defects. And this works, and this is a typical result that you can get here, where you can create arrays of single NV defects through ion implantation. The key properties of NV defect is lying in the spin properties. So the electron spin of the NV defect is a spin 1, and it exhibits a spin triplet ground state here, with a degeneracy between ms equals 0 and plus minus 1 that is lifted by spin-spin interaction by an energy of something like 3 gigahertz. There are two key properties of the NV defect, and I will not go through the detail, I'll just give you the results. So the first one is that if you just shine a laser onto the NV defect, there is an efficient polarization of the spin in ms equals 0. Starting from a thermal equilibrium with equal population in all the three spin sublevels, just by shining laser, it's possible to have polarization in ms equals 0. The second property is that the NV defect exhibits a spin-dependent photoluminescence signal. And if you want a nice picture of the NV defect, you can just consider that the ms equals 0 state is bright. There will be a lot of photons emitted out of this state, while ms equals plus minus 1 are dark state. Less photons are emitted when these states are populated. And these properties here enable the detection of the electron spin resonance by optical means. To do that, we apply a microwave field here, and when the frequency of the microwave is in resonance with the electron spin transition, it will transfer population from the bright state to the dark state, and as a result, you will have a drop of the photoluminescence signal. This is what you can see here, where there is a photoluminescence plotted as a function of the microwave frequency. When the microwave is at resonance, you have a drop of the photoluminescence by something like 25%. And I insist here that this is the spectroscopy that is performed on a single spin. If now there is a magnetic field applied at the location of the NV defect, as I mentioned before, there is a Zeeman effect that will lift the MS equal +1 and -1. And if you now record electron spin resonance spectra while changing the magnetic field, you will see, as you can see here, from the bottom to the top, you increase the magnetic field and you can see the splitting of the ESR lines. And this splitting here is directly proportional to the magnetic field felt by the NV defect. More precisely, this is what is written here, BNV, because the component that is measured is the magnetic field projection along the quantization axis of the NV defect that is defined by the direction that is linking the nitrogen and the vacancy. So here, just to show you that here the NV defect behaves intrinsically as a magnetometer. If you now want to make a magnetic microscope, as I mentioned before, you need to integrate it in a scanning probe unit, and this is the principle of a scanning NV magnetometer, where you have a single NV defect here that is grafted at the apex of an AFM tip. On top of the tip, you have a microscope objective that is used both to excite the NV defect with a green laser and also to collect the spin-dependent photoluminescence. You have a microwave antenna, which is used to perform electron spin resonance on the NV defect. And the idea of the experiment is then very simple. You just bring a magnetic structure that you scan, and at each point of the scan, you just record the Zeeman shift of the electron spin resonance, from which you extract the magnetic field distribution. So this instrument here have some key properties. First, the measurement is quantitative with a sensitivity that can go even below the microtesla for 1 second of acquisition. It's also vectorial because we probe a given projection of the magnetic field. But what is very important, I think, is that compared, for example, to magnetic force microscopy, here there is no magnetic back action. So we can consider, to first order, that the sensor in itself is not modifying the sample that you are looking at. Regarding spatial resolution, I told you that the field is probed within a detection volume that is given by the size of the NV defect, that is 7 nanometer. But in fact, the resolving power is set by the distance between the NV defect and the sample. So this probe to sample distance is really the important parameter in all experiments that will fix actually the resolving power of the instrument. So regarding experiment, this is a picture of our experimental setup. So on one side here on the right, you have a tower of piezo and scanners that hold the sample. On the other side, you have the same with the tip that you can see here. And on top, a microscope objective that is focusing here. You can see the green spot at the apex of the tip. So to engineer the sensor in itself, there are two options. In early experiments, a solution was to graft small nanodiamond, let's say nanodiamond that were a few tens of nanometer in diameter, to graft them at the apex of the tip. The drawback of this technique is essentially that you can hardly reach probe to sample distance better than 100 nanometer. A solution to that is to use all diamond scanning probe tips. So here, this is a picture that you can see here. All the blue part here is made out of ultra-pure diamonds, and you have a pillar here that will be used as a tip, and at the very apex of the pillar, a single NV defect is created through nanoscale ion implantation. So these kind of tips were introduced in the team of Amir Yacobi in Harvard in 2012, and after less than 10 years, they are now commercially available by two companies in Switzerland. The main advantage of this technique is that it's very robust, and you can really go closer to the sample surface with the probe to sample distance in a range of few tenths of nanometer. In all this talk, I will use this kind of all diamond scanning probe tips. So in the last year, there was a lot of application that have been followed, especially in condensed matter physics with NV defect. That includes the study of chiral domain walls in thin ferromagnets, magnetic skyrmions. So all that is done at room temperature, but it can also the NV magnetometer can also be operated at 4 Kelvin to study the physics of superconductors and also magnetism in two-dimensional materials. So today in this talk, I will focus on antiferromagnetic material, and for that I think I don't need to make a long introduction to motivate the study of antiferromagnets. This is really an emerging field, this field of antiferromagnetic spintronics, that rely on appealing properties of antiferromagnets for spintronics. Here I would like to bring a problem, perhaps. I believe this is a problem. The challenge here is that because the magnetic moments are compensated in antiferromagnets, the magnetic signals are extremely weak. And as a result, it's very difficult to image the antiferromagnetic order at the nanoscale. There are a few tools that you can use. The first one is advanced magneto-optical microscopy technique, for example, by some second harmonic generation, where you can image some kind of antiferromagnetic domain, but still the spatial resolution is limited by diffraction, so let's say a micron scale. To improve the resolution, you can rely on X-ray imaging and bring the spatial resolution down to a few tenths of nanometer. And if you really want to reach atomic scale resolution, you can use spin polarized STM, where you can see here an antiferromagnetic order with a resolution that is below 1 nanometer. This is a really nice instrument, spin polarized STM. However, it's restricted to UHV condition, and also you need a conducting sample to operate the STM. So in our case here, we will use NV microscopy, as I told you, so the spatial resolution is in the range of 50 nanometer, and the key point here is that it is a tabletop experiment that can be used in ambient condition on any kind of magnetic sample. In the last years, we have used this NV magnetometer to study antiferromagnet, and one of our focus was to study a well-known multiferroic material, bismuth ferrite, that is both a ferroelectric and an antiferromagnetic material at room temperature. What is interesting in this material is that both orders are coupled by magnetoelectric coupling, and this is what is represented here. You have, for example, here the orientation of the polarization and the propagation of a cycloidal antiferromagnetic order here that is propagating perpendicular to the polarization. And here the idea of this kind of material is that you can essentially modify the magnetic order just by rotating the polarization vector, so having a control of magnetism by electric field. So we first started a few years back to try to image this kind of cycloid in bismuth ferrite, and this is a typical result that we got a few years ago. And you see indeed that there is a magnetic field modulation with a propagation vector here k that is indeed perpendicular to the polarization, to the ferroelectric polarization. But what is nice here, besides being the first time that this kind of cycloid is observed in real space, is now if you rotate the polarization with electric field, then indeed you can verify that you can also rotate the magnetic order thanks to the magnetoelectric coupling. This kind of experiments have been done in other type of antiferromagnetic material, for example in chromium oxide by the group of Patrick Maetinsky and in Basel, and the one of Christian Degen at ETH. And in this work here, I have shown that they can image domain wall in this magnetoelectric antiferromagnet. Still, there is a drawback here, is that intrinsically the NV magnetometry technique is restricted to samples that produce strong enough magnetic field. So if you consider a perfectly compensated antiferromagnet, then you won't be able to image its structure because it will produce no stray field. So we wanted to go through this problem, and one solution was proposed by the group of Jaroslav Charkovniak. The idea is pretty simple, is to image spin structure by detecting the magnetic noise that they produce rather than a static magnetic field. So magnetic noise produced by spin waves that on average produce a zero field, but produce a variance of the field, a noise that you can detect with an external sensor. So the idea is pretty simple. You consider an antiferromagnetic material. Here there is thermal agitation, or let's say spin waves or magnons, and then you will bring your NV spin here above the sample to measure the magnetic field noise. And the idea here, and this is what is proposed in this paper, is that at the location of a domain wall, for example, there is an excess noise because there are additional magnon modes that can be populated, and at this particular location, you expect to detect an enhanced magnetic noise with your quantum sensor. So the first question we can wonder is how to measure magnetic noise with NV defect. So for that, I need to come back a bit on the photophysics of the NV defect in diamond. So I just show here the spin triplet ground state. And as a reminder, ms equals 0 is a bright state, and ms equals plus minus 1 is a dark state. And you can polarize the system by optical pumping in ms equals 0. So let's consider that the system is initialized in ms equals 0, all the population are there, and then we can let him evolve in the dark, this is a free evolution, to come back to his thermal equilibrium. The typical time required to reach the thermal equilibrium is called the longitudinal spin relaxation time, T1. And what is interesting here is that this spin relaxation time is directly linked to the noise power density at the electron spin resonance frequency. To make it short, if you have some noise at the ESR frequency, then it will boost a relaxation, and you will have an enhanced relaxation in the presence of noise. So how we measure this T1 with NV, this is pretty simple. So we just have a first laser pulse to polarize the system in ms equals 0. We are in this situation. Then we wait for a certain delay, and then we apply a second pulse, a readout pulse, that will read out the population of the NV defect shows spin-dependent photoluminescent signal. So this is a typical result that you can get for a single NV defect without any magnetic noise in the surrounding. You end up with a T1 time of about 1 millisecond, which is essentially limited by phonons in the diamond matrix. If now you apply noise in the vicinity of the NV defect, you can see that indeed you shorten the T1 time here by 1 order of magnitude. So this technique here is called relaxometry. It has been used for many purposes. For example, to study Johnson noise. This is the thermal agitation of electron in metals, for the physics of spin waves as well. And it was also used to detect magnetic nanoparticles down to the single particle level. Still, there is a problem if we want to integrate this kind of measurement in a scanning unit, is that the measurement of a T1 curve here is extremely long. Essentially, to take a curve like that, you need a few hours of acquisition, so it's not possible to imagine to make a scanning unit where at each point of the scan we measure T1. So we need to rely on another physical protocol to measure the noise. And for that, I would like to show you that there is also a quenching of the photoluminescence of the NV defect that is induced by magnetic noise. So for that, we again rely on a simplified two-level system where we have the bright state and the dark state, and we have the competition between two effects. The green arrow here shows the optically induced spin polarization in ms equals 0. So essentially, this is the optical illumination that brings the population in ms equals 0. And this is in competition with the longitudinal spin relaxation rate here, gamma 1. And we have essentially two different cases. When gamma 1 is much smaller than gamma p, then we have a very efficient polarization in ms equals 0, and as a result, we have a high photoluminescent signal. On the other hand, when gamma 1 takes over gamma p, then we have equal population in all the spin sublevels, and as a result, we have a lower photoluminescent signal. So if you make the calculation, then you can see that you plot the photoluminescence as a function of T1, you can see that indeed, when T1 is decreased, or gamma 1 increases, you have a drop of the photoluminescence by something by 20%. And of course, if you increase the optical laser power, you increase gamma p here, so the position where you can see the drop in photoluminescence is shifted towards lower value of T1. So we just verified that experimentally. This is what you can see here, where we have the photoluminescence signal as a function of T1. For that, we use the calibrated magnetic noise source, and indeed you can see that you have a strong drop of the photoluminescence when T1 is decreased. So here we have now a very simple way to measure location in the sample where you have magnetic noise that just rely on measurement of the photoluminescent signal. So the idea is simple. If there is noise, then it will drop T1, and as a result, lead to a drop of the photoluminescence. So this is this process that we will use in the following, and just to show perhaps a kind of proof of concept experiment, we decided to study synthetic antiferromagnets. So these are not intrinsic antiferromagnets, this is just two ferromagnetic layers that are coupled by a non-magnetic spacer antiferromagnetical. So this kind of system can be somehow considered as a model system that can be used to emulate the physics of antiferromagnets. But what is really nice with synthetic antiferromagnets that we can really tune their magnetic properties by changing the thickness of the different layers. So in our case, we use two cobalt layers here with ruthenium and platinum, and we use perfectly compensated synthetic antiferromagnet, meaning that the thickness of the two cobalt layers, which are the ferromagnetic layers, are exactly the same thickness. So this sample has been optimized in the group of Vincent in CNRS Thales, and this sample led to the first detection of antiferromagnetic scatters. So we started with a sample in which the thickness of the cobalt layer was chosen to have out-of-plane magnetic anisotropy, and we decided to use our MD magnetometry to try to image domain walls in this sample. So now this is the principle of the experiment. We rely on a diamond tip here, but we don't have any kind of microwave to apply. We just excite with a green laser and collect the photoluminescence. And this is a typical result that we can get on this sample. You see dark quenching lines here that are essentially localizing the position of the domain walls in the sample. To verify here that the quenching is indeed induced by magnetic noise, we did measurement of spin of the longitudinal spin relaxation in two conditions. First, by engaging the tip above the domain and then above the domain wall. And these are the results here. In blue, you can see the measurement when the NV is engaged on the domain. You have a T1 of about 120 microseconds. While moving to the domain wall, there is a sudden drop of the relaxation, and T1 is brought to 20 microseconds. So here we are sure that this quenching that we see is indeed induced by magnetic noise, and this is supported by this spin relaxation measurement. So essentially here, our NV defect really behaves as a quantum sensor. We essentially use its interaction with the environment, here with the magnetic noise, and we measure this characteristic coherence or relaxation time to image magnetic noise in the sample. So now we can wonder what is the origin of the noise, and essentially this is a noise that is originating from thermal magnets that are localized at domain walls. So for that we relied on micromagnetic calculations that were performed by Jacques and Kim at C2N, and essentially Jacques calculated the dispersion relation of the spin wave both in a uniform domain and in a domain wall. So in a uniform domain, so this is the dispersion relation here, and what is interesting is that there is a gap here in the dispersion relation that is essentially given by the anisotropy in the sample, and what you can see is that if you plot now the value of the electron spin resonance frequency of the NV defect, you can see that there are no magnets at this frequency, and as a result it's not possible to have magnetic noise at the electron spin resonance frequency. So although there are some magnets populated, they will not produce a noise that will be felt by the NV defect. If we are going to the domain wall, at the domain wall the spin dispersion is gapless. This is something that is known both in ferromagnets and in synthetic antiferromagnets. And as a result, you can populate some magnet modes here that will have a direct impact on the spin relaxation time of the NV defect. So you can also calculate what would be the noise map, so essentially the strength of the noise, and you can see here that the noise is indeed much stronger at the location of a domain wall. So this is essentially what we see in our experiments. So now we decided to do a bit more and try to look at other spin texture in this synthetic antiferromagnet. And the first sample that we looked at is a synthetic antiferromagnet with vanishing anisotropy. So here essentially the cobalt layer were adjusted in order to have a vanishing anisotropy in the sample. And in this case, you expect the stabilization of a spin spiral. And this is indeed what we see here. So this is a chaotic spiral because there are a lot of pinning sites in the system, but you can see that we can see the spiral with a periodicity that is something like here about 250 nanometers. This spiral is interesting because now, as soon as you have this spiral state, then you can try to bias the spiral to obtain skyrmion. And for doing that, you add a bias layer here that will act as an internal magnetic field that will collapse or turn the spiral into skyrmion, as proposed in first paper from Vincent group. And this is indeed what we see. So after putting the bias here, we can see that we have isolated dark spots here that correspond to magnetic skyrmion. So here, magnetic skyrmion, at the location of magnetic skyrmion, we have an excess noise, and this is the way we can observe this skyrmion in our sample. By just taking line cuts, we can see that we have a distribution of the size of the skyrmion that is around 80 nanometer, and we believe that this is essentially limited by the distance between our NV defect and the sample. So here, essentially, what we have done is to introduce a new way to measure spin texture in antiferromagnet that rely on measurement of magnetic noise rather than a static magnetic field. And that might be useful for studying antiferromagnetic material that are perfectly compensated and those that will not produce stray magnetic fields. So as a conclusion, I just want to show you that the magnetic field, the NV defect, sorry, can be used as a magnetic field sensor, either for static magnetic field, but also for magnetic noise, and that can be used for studying antiferromagnet, for example, bismuth ferrite here, or synthetic antiferromagnet. But you can do even more with the NV defect. You can also measure electric fields through the Stark effect, and also temperature. And here I think that electric field might be a really useful tool, especially to study multiferroic material, where you could imagine to measure in a row the magnetic field distribution and also the electric field distribution to try to study the correlation between the ferroelectric and magnetic order. So with that, I'm done. I would like to thank the people that work with me on this project. So in Montpellier, this is essentially Aurore Franco, Florentin Fabre, Angela, Rana, Isabelle, and Maxime. And I would like also to thank all the collaboration that we are involved in, that are really at the core of this project, especially the team of Vincent Cross, Stéphane Fusil at the CNRS Thales unit, Michel Guérin and Jean-Yves Cholot, the team of Jowon Kim at C2N, and Nicolas Jaouen at Soleil. And with that, I would like to thank you for your attention, and once again, I hope to meet you in person very soon in the conference. Thank you.